Chapter 8. Lots of discussion of concentration here in Chapter 8. So let's start by talking about what a solution is. This is something that involves a solute and a solvent. And a solute is generally going to be the thing that you have less of, and a solvent is going to be the thing you have more of. So if you think about, say for instance, making lemonade, you have a solvent of water, and you have a couple of different solutes. You've got some lemon juice in there, and you've probably got some sugar as well. And if it's lemonade that you're not making at home, it's probably got some artificial color going in there too. But when you think about it, the sugar in the lemon juice, there's much less of those than there is the water. So water is the solvent, and sugar and lemon juice are both two different solutes. When you mix them all together, you should get a homogeneous mixture, and we call that a solution. You can have liquid-liquid solutions, you can have gas-liquid solutions, you can have gas-solid solutions, you can have gas-gas solutions. For instance, air, as you breathe in and out, what you breathe in is a solution of gases, nitrogen, oxygen, and a variety of other things. 14-karat gold is a solution, and stainless steel are both examples of solid-solid solutions. One thing that really kind of controls whether a solution happens or not, or maybe better to put would be a general observation, is that like dissolves like. So polar things dissolve polar things, nonpolar things dissolve nonpolar things, and the two don't mix together. So if you think about trying to make a vinaigrette for salad, you have your vinegar, which is water-based, and you have your oil, which is nonpolar, and you have to shake them really hard in order to get them to mix. And if you leave them on the counter long enough, what happens? Well, it separates back out, and you have a heterogeneous mixture, and it didn't dissolve. So we can talk about solubility, or the ability of something to be dissolved, in terms of a couple of different terms: unsaturated, saturated, and supersaturated. And these terms you may have heard before when people talk about fats. So like, for instance, saturated fats or unsaturated fats. This is a different type of saturation. When we talk about fat saturation, we're talking about how many carbon single bonds and carbon hydrogen bonds there are. When we're talking about saturation in terms of solubility, we're talking about, does the solvent hold all the solute that it possibly can at that particular temperature? Let's go back for a sec. So unsaturated means that the solvent that I have can take more solute. Saturated means I've dissolved exactly the amount of solute that the solvent can hold, and supersaturated means I've managed to dissolve more solute than the solvent can hold at that temperature. And supersaturated solutions are actually incredibly unstable. And what you have to do to make a supersaturated solution is take your solution and heat it up. So when you think about this, if anybody drinks iced tea and you've tried to dissolve sugar in iced tea, you reach sort of a maximum level of sugar that you can put into the iced tea, and then after that, you're pretty much just sipping sand. Versus hot tea, you can dissolve a lot more sugar in. So this is the same idea behind supersaturation. The saturation level is temperature dependent. So I can take a solution, add my solute, and then heat it up and dissolve more solute, and then cool it down. And if I can keep the solution stable at that new temperature, I have a supersaturated solution, something that I've dissolved additional solute in. Different compounds, different ionic compounds, have different solubilities. And in your textbook, you have this chart, which looks at ionic compound solubility. And just so you can reference it for later, let me find the page this is on. Oh, it's on page 197. And you can see here that we can predict whether something's soluble or insoluble based on this information. So soluble compounds are pretty much listed in this first half of the table, things that are generally soluble are here. There are some exceptions. For instance, if I had silver chloride, I would go over here and find chlorides and see, well, generally they are soluble, but important exceptions, there's silver, which tells me that silver chloride is actually insoluble. Insoluble means it can't dissolve. I try and mix it with the water, and it just stays a solid, so I don't get a solution. Insoluble compounds are listed generally in the next table. So these are things that are generally insoluble. So if I have iron to carbonate, I can find carbonates and see, oh yeah, they're generally insoluble. There are some exceptions. Iron is not one of them. So therefore, iron to carbonate would be insoluble. If I had sodium carbonate, however, sodium is one of my group 1A metals. It's one of the exceptions to the general rule that carbonates are insoluble. And so sodium carbonate would actually be soluble. So, are the following compounds soluble or insoluble? Go ahead and crack your book open to page 197, hit pause, and decide whether these are soluble or insoluble or not. Okay, so calcium sulfide. We're looking for, in the list of of elements, we're looking for either calcium or sulfide. So as I go through here, I find sulfide is generally part of an insoluble compound. There are some exceptions, groups 1A, groups 2A, and ammonium ion. Now calcium is in group 2A. So that means that calcium combined with sulfide is an exception to sulfide's general insolubility. So therefore, calcium sulfide is soluble. Silver chloride, we actually already worked this one together, is insoluble. And sodium hydroxide, we look through our table and find groups 1A are generally soluble. In fact, there are no exceptions to that rule. So your alkali metal compounds are always soluble. So this is soluble. Saturation, whether something's saturated, unsaturated, or supersaturated, is a general way of talking about solubility. We can get more specific and talk about specific concentrations of solutions. And we do this using one of two methods, either a percent concentration or molarity. Percent concentrations are just like your basic percent. If you think about taking the percent of, let's say, people who want to be nurses in our Chemistry 121 classroom, what you would do is count up the people who want to be nurses and count up the total number of students. And you take the number of people who want to be nurses and divide by the total number of students and multiply by 100%. Same idea when we get to percent concentration. We look at the amount of solute and we divide by the total amount of stuff, so otherwise known as the total amount of solution. Multiply the thing by 100% and that gives you percent concentration. These can be mass percents, volume percents, or mass volume percents. And what that means is, let's take mass percent for example. That means that I have mass of solute divided by mass of solution. Times 100%. So essentially I'm just using this generic formula here and applying whatever units it's told me. So for mass percent, it's mass of solute over mass of solution. For volume percent, it would be volume of solute over volume of solution. And mass volume percent actually has specific units. It's always grams of solute over milliliters of solution. So we're going to look at a couple different examples of this. And the way to look at these examples so that you can sort of see the pattern and then apply it to your homework and then apply it to when you're faced with these questions on a quiz, is to look at, is the question asking you for a solute, solvent, or solution? And this first example, we can see says, how many grams of NaCl are needed to prepare 650 grams of 5.7 mm% solution? So it says, how many grams of NaCl? So that's really saying, how many grams of solute? I know this as well because it tells me I have 650 grams of solution, and it also tells me what the percent concentration is. So this example, I'm being asked to solve for solute. Now, your percent here is actually hiding a unit conversion because percents are always parts per 100. So 5.7 mass percent is the same as saying 5.7, and any mass unit I want to choose, so I'm going to choose grams because it's convenient, of solute, which in this case is NaCl, divided by 100 grams of solution, right? That's what my definition of percentage tells me. 5.7% is 5.7 parts per 100 total parts. And in this case, my parts on top are solute and my parts on the bottom are solution. So I can use this as a unit conversion. I'm told that I'm starting with 650 grams of solution. So I can think about this as, well, I need to cancel solution and I need to get to NaCl. So therefore 100 grams of solution goes on the bottom and 5.7 grams of solute goes on the top. Now, if you're really comfortable with percentages, you probably don't need to do this. But my experience with Chemistry 121 students is that percentages are not something we're always particularly comfortable with, whereas we have done a lot of practice doing unit conversions. So at this point, I just need to pop things into my calculator. It's 650 times 5.7 divided by 100. So I end up with 37.05, and I only have 2 sig figs, so 37 grams of NaCl are what I need to make 650 grams of 5.7% solution. Example number 2, how many grams of water are needed to prepare 50.0 milliliters of 9.78 volume percent solution of KBr? Now notice in this question, what is the question asking for? Solute, solvent, or solution? Well, it's asking for grams of water, which tells me that it's asking for solvent. It tells me I need 50 milliliters of solution, and that solution is 9.78 volume percent, KBr. So let's take our percent out and look at its unit conversions. We just learned that we can write this as 9.78 milliliters of KBr. I'm choosing milliliters. Choosing milliliters because I've got milliliters here. Now, this says grams of water, and really what I meant was milliliters of water. So go ahead and cross that out. So 9.78 milliliters of KBr, going back to my percent here, is part of 100 milliliters of solution. So that's our unit conversion. There is another unit conversion hidden in here. If I have 9.78 milliliters of KBr and 100 milliliters total, then I should be able to figure out how much water I have in that by taking 100 and subtracting 9.78. Because this is my solution, this is my total. If I subtract the solute, then I should be looking at the solvent. So 100 minus 9.78 gives me 90.22 milliliters of water. So that's 90.22 milliliters of water per 9.78 milliliters of solute, or per 100 milliliters of solution. Now, which of those relationships is what I want? Well, I know that I need to use the solvent one because I asked for water. And I also know that I want to use solution because it told me I had 50.0 milliliters of solution. So 50.0 milliliters solution is where I'm going to start. And now I need a conversion factor that relates solution to water. Well, I know from here that my percentage told me I had 100 milliliters of solution. And from my calculation, I know that that solution contains 90.22 milliliters of water. So in terms of my units, milliliters of solution cancels, and I'm left with milliliters of water. So 50 times 90.22 divided by 100 gives me 45.1 milliliters H2O. So this was an example that gave me solution and asked me for solvent. Example number 3. How many grams of solution are prepared when 32 grams of water are used to make a 5.0 mass percent solution of lithium chloride? So now I'm being asked for grams of solution. I am given the water, and I am given the percent in terms of a mass concentration. So my percent is the same as saying 5.0 grams LiCl is to 100 grams solution, right? Because that's my total. I'm going to have to start with water, though, because this gave me 32 grams of water. So that means that I need a conversion that involves water. Well, if I have 100 grams of solution and 5.0 grams of that is solute, then the remainder must be water. So take my solution, subtract my solute, gives me 95 grams of water. So for every 5 grams of solute, I have 95 grams of water. For every 100 grams of solution, I have 95 grams of water. Since it asked me for grams of solution here, I'm going to start with my 32 grams of water and use the relationship between water and solution. 95 grams of water is equal to 100 grams of solution. So my grams of water cancel out, and I have 32 times 100 divided by 95, which gives me 33.6, which I only need 2 sig figs, so this becomes 34 grams solution. So notice here in my unit conversion, I treated this unit conversion just like all my other unit conversions, where I can put whatever unit I need on the bottom of the fraction and whichever one I need on the top of the fraction. Excuse me. So I can flip those as needed based on whatever unit conversion I need to make. The other concentration unit that we'll be dealing with is molarity. And molarity is defined as the moles of solute divided by the liters of solution. So molarity brings in moles for us. Our first example with molarity, and molarity you can think of as a unit conversion as well. So I have how many liters of solution are needed to make a 4.50 molar. So capital M means molarity. That's what that capital M is telling me. Containing 90.0 grams of sodium sulfate. So this, remember, was moles of solute per liters of solution, which, just like our percentages, contains a unit conversion. 4.50 molarity is the same as saying 4.50 moles solute to 1 liter solution. So the question asks me how many liters of solution are needed if I'm going to make this solution out of 90.0 grams of sodium sulfate. Molarity is going to allow me to transfer between moles of solute to liters of solution. So it kind of makes sense that my mass that I have of sodium sulfate, that my first step would be to go to moles and get out of grams. So to do that, I need the molar mass of sodium sulfate. So 4 oxygens plus a sulfur plus 2 sodiums. And let's see, sodium is 23. Gives me 142.07. And that's per mole of Na2SO4. So that gets me out of grams, but the question asked me for liters of solution. So now that I'm in moles, let's get rid of my grams so we're not confused. I can use my molarity conversion that I had up here to change from moles of solute to liters of solution. And since moles were up here in the numerator, then they have to go down here to cancel out. So 4.50 moles solute, 1 liter solution. And now I have units of liters of solution, so it's just a matter of putting into my calculator. So 90 divided by 142.07 divided by 4.5 gives me 0.14077, and I need 3 sig figs, so 0.141 liters. That's my answer. Let's do a second example. How many moles of sodium ion are contained in 330.0 milliliters of 0.05 molar sodium phosphate solution? So notice, this example, we're being asked about solute. In the first example, we were being asked about solution. We still can use our molarity term here as a unit conversion. 0.05 molarity is the same as saying 0.05 moles solute, which in this case is sodium phosphate, per 1 liter solution. So I'm being asked for moles of sodium ion. Well, that's going to be interesting because this is a molarity of sodium phosphate. So I'm going to have another step in here to get to sodium ion. But let's see where we're going to start. We have 330 milliliters of solution. So let's start there because that's the number that we're given. Here's my solution. I need to get to moles of sodium ion. Well, my molarity will allow me to get to moles of solute, moles of sodium phosphate. And then, if you'll recall from chapter 6, hidden in the formula Na3PO4, remember, was the unit conversion that 3 moles of sodium ion equaled 1 mole of Na3PO4. So that means if I can get to moles of sodium phosphate, then I can use that conversion to get to moles of sodium. So back down here, I'm in milliliters of solution. My molarity conversion has liters of solution. So I need to get out of milliliters into liters. There are 1,000 milliliters in 1 liter, something you should have memorized from the blue sheet. This is still solution. My milliliters cancel. Now I'm set up to use my molarity. 1 liter of solution goes on the bottom, and 0.05 moles Na3PO4 goes on the top. So liters of solution cancel out. There's my moles of sodium phosphate. My last step is to get to moles of sodium ion. So I'm going to use my unit conversion that I developed up here based on the formula, that 1 mole of Na3PO4 is equal to 3 moles of sodium. And at this point, my moles of sodium phosphate cancel out. I'm left with moles of sodium. So just put it into your calculator. 330 divided by 1,000 times 0.05 times 3 gives me 0.0495. But I only have 1 sig fig. It was in my molarity. So I should only have 1 sig fig in my answer, and that actually comes out to be 0.05 molar sodium. Moles sodium, sorry. Ion. So there's my answer. Dilution. This actually is a vast part of what you will probably do in terms of applying chemistry knowledge to the real world. Dilution is a pretty handy thing to know how to do. You dilute things when you make juice in the morning, if you make it from a frozen concentrate. You may be diluting medications as a nurse or a dental hygienist or any of the medical fields that you're going into. Even if you're not actively doing that, there's going to be an expectation when you get into those programs and fields that you know how to do it. And so they're going to check that you know how to do it. So this is a pretty practical application thing here. Dilution basically is the process in which you add more solvent to a solution in order to decrease the concentration. So dilution with water does not alter the number of moles of solute present. In fact, dilution with water never alters the amount of solute you have. It alters the amount of solvent you have. So that means that the moles of solute before the dilution will equal the moles of solute after the dilution. And so we can set up our molarity equation by solving for moles and then just cut out the moles in the middle. And what this gives us is a dilution equation. The molarity of our first solution times the volume of our first solution will equal the molarity of our second dilute solution times our new volume. So let's look at an example. What is the concentration of a 5.60 molar solution if 35 milliliters of water are added to a 60.0 milliliter sample? So let's list out what we're given. We know this is a dilution problem because water is being added and my volume is changing. And it's asking me for a new concentration. So that means I'm going to use M1V1 equals M2V2. And if you check your blue sheet, you'll see that this is one of the equations that you're responsible for memorizing. Given that I want to use this equation, it makes sense to isolate and list out what information I'm given in the problem. So my first molarity is 5.60 molar, right? That's what I start with. And it says 35 milliliters of water are added to a 60.0 milliliter sample. So my initial volume is 60.0. My second molarity, I don't know. It asked me, what is the concentration after I add this water? So that's what I'm going to be solving for. The new volume is going to be my sample that I started with, 60, plus the 35 milliliters of water that I added for 95 milliliters. So now I just need to plug things in. My M1V1 equals M2V2, I can solve for M2 by dividing both sides by V2. So I just plug in my molarity, 5.60 molar, times my first volume, which was 60 milliliters, divided by my total volume of my new sample, which was 95 milliliters. Notice here I can use milliliters because I've got milliliters on top and milliliters on the bottom, and they'll both cancel. We can't always use milliliters when we're dealing with molarity because it is per liter of solution. But in this case, because my volumes cancel, I can leave them in whatever unit I want. So now go ahead and put it into your calculator. 5.6 times 60 divided by 95 gives me 3.5. Yeah, because I only need 2 sig figs. 3.5 molar. So notice the concentration went down from my original concentration, which makes sense because I added water. So that's it for Chapter 8. Your homework, and I really encourage you to do these problems, are going to be 1 through 56.